Okay. So, how can we deal with this thing? I'll try putting it over here. So anyways, now, hopefully you recognize that with this, we have our R standard, and we have our device under test here, and we have a, let's see, come on, you. We have a V in, and we have a V out. And if you want to get picky, there's our where we might put a voltmeter. And so we're used to a voltage divider. Is R2 over R1 plus R2 times V in. And we should get used to this because when we work with any of these circuits, what we eventually create is V out over V in. But first of all, let's deal with something now because we're going to have three things to look at: a resistor, and that's our R experimental, and we have a capacitor, and we have an inductor. So when we put an inductor into the box labeled device under test, how do we deal with it mathematically? Because we know, if we know anything, is that an inductor has a value called L that goes with it, and it's expressed in henries, if we know anything, and that's not an ohm. And when we look at our voltage divider equation, we expect something to be in ohms. So, but there's AC all around us. Capacitors and inductors are useful with AC. They're not very useful in DC. It's really weird that the capacitor lab in Physics 2200 is done with DC. I'm going to have to just break down and write that lab up the way it's supposed to be done. But anyways, so what we need is a generalized resistance. And you've heard me use this word. It's called the impedance, Z. And Z is equal to R, the real resistance, plus I times something called the reactance. And that's a chi, Greek capital letter chi. So that means, first of all, if we remember anything about complex numbers, if we want to know the magnitude of Z, we treat this as a triangle, and the reactance is on the imaginary axis, and the real part is the real axis. And we add these things in quadrature. And that means we do R plus I chi, oh, I'm not doing that very well, am I? Times R minus I, because what happens is if you were to multiply I chi times I chi, you get a minus 1, and we need to get rid of that. And so that's the complex conjugate, right? Everybody remembers that? Pretty straightforward. Oh, yeah, like. But generally speaking, people just say that the magnitude is equal to R squared plus this, and we'll put in the word total here, because we have to learn how to add together the reactance of a capacitor and an inductor. Okay? So yeah, let's just go right in your logbooks. Everything in your logbooks. Okay? And I am recording this with the screen, and I'll save these slides, of course. I want to try to get good at writing things down in our logbooks quickly, for example. Okay, so the reactance of a capacitor equals a minus, which the minus we generally ignore, but first of all, let's do it like this. Omega C, which is equal to, a more familiar, 2 pi times C. Oops. In this case, 2 pi F. Because you may remember that 2 pi F times C. So omega is in radians per second. F is in cycles per second. So there's 2 pi cycles for each radian, 2 pi radians for each cycle, one time around. So that means that omega equals 2 pi F. Hopefully that sounds familiar. And then the reactance of an inductor is 2 pi LF. So notice then that at low F, Z of the capacitor is large, and Z of an inductor is low. And at high F, the Z of the capacitor is low, and the Z of the inductor is high. These are things that you should memorize, like the rules of thumb about series and parallel resistance. Because this will help us when we look at a circuit. If we remember that simple thing, like 1 over the reactance or the impedance of a capacitor goes as 1 over F. So at low frequencies, the capacitor is going to want to block DC. It'll tend to be a high resistance. If it's in line, then it will be a blocker. But basically, what you remember is these at low frequency, the Z of the C is high, Z of the L is low. After we finish this, we're going to dive right into Chapter 2. We've covered enough of Chapter 1. The only thing I need to do it was a toss-up, but I think this is pedagogically better, or at least in practical terms, because we're working on this right now. In terms of order of things we've done, the full Thevenin derivation would be appropriate, right? But it's less confusing if I do this now, because we're right about to do this, right? Take these measurements. So next time I'm going to get into the Thevenin derivation, and then after we finish the oscilloscope lab, we're going to dive into Chapter 2. And in Chapter 2, you're going to be making high-pass and low-pass filters. And if you get this down in your head, this slide, you'll be much easier to look at a filter and know right away whether it's high-pass or low-pass. And then, of course, there's some things you have to calculate for details. But as I just said, they're details. Oops, I wanted to duplicate that. So, in the sense of baby steps, let's take a look now at the we're going to be doing not four things actually. We're going to be doing 4 voltage dividers. One of them is going to be our standard and the capacitor. One is going to be our standard and the inductor. One's going to be our standard and our experimental. And then one's going to be our standard and an LC. So this is always going to be Z1, and this is Z2, which is AKA the device under test. Very typical circuit. You make a voltage divider with the resistor and the device under test. What happens is that if you measure the voltage across our standard, it gives you, if you remember the first exercise we did, if I get the voltage across our standard, I know what the current is. And that's why this is done. You don't even have to know what a voltage divider is to know that I can get the voltage across the device under test. With the voltage across our standard, I get I total, and then I can calculate the resistance of the device under test. We've done it before. It's a statement engineers make that resistors turn voltages into currents. We didn't say it explicitly before. I'm just pointing it out to you. What we're going to do now is we're going to learn to do this the standard way, where you measure V out and V in. But the first thing we're going to do is we're going to calculate what V out over V in is supposed to be. So this one's always going to be Z1. This one is always going to be Z2. So in the case of the first one, RC, Z2, it's going to equal to 1 over 2 pi FC. Now I've dropped the minus sign because basically, remember, it was minus I. And strictly speaking, when I write it this way, I'm talking about the magnitude. So I would have multiplied, it would have been square root. Now, well, let's slow down on that one. I don't want to throw too much at you at once. When I take the magnitude of minus I times 1 over 2 pi FC, this is what you end up with. I encourage you to do the complex algebra. So that means then, remember the basic voltage divider equation. Come on. Oh, I see, I'm still erasing. V out equals to Z2 over Z1 plus Z2. Times Vn, of course. So how does one calculate this mess here? Well, then this would become 1 over 2 pi FC divided by R standard squared plus 1 over 2 pi fc squared to the half power. And usually what you do, just for the p's and q's of it, is that you square this and square root it, but you can see where that's just going to come up with the same thing. Suspected spam caller. What happens is people generally drop the i's and they just try to do the bookkeeping in their head. If you write it out the way I just did, that way, if you put the I in or don't put the I in, it comes out to the same answer. Okay. Can I, Laura?
Where does that expression you just wrote, where does it come from?
Oh, if you take and you're going to measure it today, if you measure the Z2 as a function of frequency, you figure out that the impedance of a capacitor is 1 over 2 pi fc. Is that what you're asking me?
Yeah, but the larger expression.
Over here, the sloppiness here?
No, just the entire thing.
Sorry?
The 1 over 2 pi plus c squared. And then
Oh yeah, that is Z1 plus Z2. I have to add them in quadrature because one's on the real axis and one is on the complex axis. That was from here. Yeah. Yeah, see it right here?
What does quadrature mean?
Adding in quadrature means squaring it, adding it, and square rooting it. I know. Good, thank you for that. I hate when people use jargon. Even in high school and college, I was always the stinker who asked, what does that mean? Of course, I used to get my teachers mad at me. Because it's pretty dumb. You should never use a word that you don't know the meaning of. Or if you make a slide to give a talk, you better be damn sure that every single thing on that slide is something you can explain. If somebody points out something on your slide that you can't explain, you look bad and you get bogged down. Okay, so here I was. All right, so the next step, just yell if you want me to go back. Okay, going back to this one. Oh, I'm sorry. Write it down. I'd rather you write it, take a picture, that's fine. But I'd rather you write it down in your logbook, because it'll stick in your brains better if you write the notes. Yeah, my headache's coming back from talking. I had some dental procedure on Friday. It's turned out to be more than I bargained for. Okay, so there is the RC circuit. The next one would be the RL circuit. So, of course, this is always Z1, and this is always Z2 no matter what it is. And we know it's Z2 divided by Z1 plus Z2. That's the voltage divider equation, which is V out over V in. That's how I always remember it. Excuse me. So the impedance of an inductor, in fact, inductors An ideal inductor has a resistance of 0, and it's not possible. So you're going to see some incongruities in your graphs, and it's due to the fact that an inductor actually does have a little bit of a real part. But for now, we're going to ignore it. So this means we have, and this is 2 pi FL. This one is a little less messy. 2 pi FL divided by r squared plus 2 pi FL squared, and the whole thing square rooted. And notice how the way they add Z1 plus Z2, they're in series. We'd have to go through some more gymnastics if they were in parallel. And we'll be doing that eventually, but not today. All right. The ratio, we're going to be measuring both of them today, but when you quote to somebody, it's always quoted V out over V in. If you think about it, then who gives it? Nobody cares what V out and V in actually are, right? It's a normalization technique. Normalization is just preparing data that you can compare apples to apples. So it's much easier to quote the V out over V in. In fact, it's even more formal. We're going to learn how to take the logarithm of it, a special logarithm, and that's what people actually quote. We're going to learn about decibels and things like that. Laura?
Why are the bottom terms in the fractions squared and then?
Well, strictly speaking, even the top part is squared and square root. Because if you truly were doing it, remember it's I times 2 pi FL. To get the magnitude of that, you have to multiply this times minus I 2 pi FL, and then you square root it. Oops. In this case, effectively, it's the same thing. I don't have the I up here. It's complex algebra. You should review it a little bit. Whenever you want when you want to quote the magnitude of a complex number, you multiply the number times its complex conjugate. In the case of the reactances, there's no real part. So let me try to write this a little more neatly. So, and to be real fair, the Z of L is equal to I times chi of L, right? So if I want the magnitude of Z of L, that equals I times chi of L times minus I times chi of L, and then I square root it. So I multiply the imaginary number by its complex conjugate, and then I do the square root. You notice that I times I is a minus 1, but then I have a minus sign, so it's a plus 1. Chi L squared, and 1/2. So because it's kind of a trivial result, when people do this voltage divider equation, they tend to just write it like this and sometimes don't even bother with the square and the square root. And then if we go now to the RR circuit, so of course that one is the easy one, Z2 over Z1 plus Z2, and that's simply going to be R, and that's our experimental, divided by R standard plus R experimental. Okay, so the last one is a little tricky, not overly so, because it's the LC is we call it a series LC circuit. So the device under test is going to be a capacitor and an inductor in series. So this is going to be Z1, ZL plus ZC. And since we're saying that they're both pure reactances, we don't have to worry about the quadrature part. It's just going to be chi L plus chi C. But we have to remember that this is equal to 2 pi FL, and this is equal to minus 1 over 2 pi FC. So ZLC equals to 2 pi FL minus 1 over 2 pi FC. And in fact, to be strict, we have to add them like this. Yeah, it's easier if we want to just say chi LC, that's equal to 2 pi FL minus 1 over 2 pi FC. I have a tendency to mix those together. That way this is better this way. So to get the Z2 over Z1 plus Z2, that's the chi L plus chi C squared and square rooted. Now, let me think this one for a minute. Does that make a difference? I don't think so. I don't think, well, no, you don't have to do it that way. Okay. You do have to do it, though, down below. So it's R squared plus chi L chi c squared square root. Laura,
I think what I'm not understanding is why do you take the square and the square root after adding the two terms?
because these two guys are both on the complex axis, so they can be added algebraically. But since because the real part and the reactances are on the different axes, they have to be added in quadrature. So again, at the top, you don't have to square and square root.
Does the denominator of the right-hand side of that equation represent z1 plus z2?
That's correct. That's right, here.
Which part of it is z1 and which part of it is z2?
This is Z2, 1, this is Z2. The device under test is always Z2.
Then why is the square root out containing both of them? Why don't we square them separately?
Oh, because that would be the same as just adding them together. R is on one axis, and the chi's are on another axis. So it's the Pythagorean theorem.
Okay.
Sorry, I didn't say those words before. It's related to phasors and the I and the V vectors when you look at AC. I didn't want to get that heavy just yet. I'm just showing it to you without a lot of proof. Question?
Why is chi c negative?
Because when you look at the phase shift between the voltage out and voltage in, you'll notice that the capacitor shifts it one way and the inductor shifts it the other way. When the two of them are equal to each other, it doesn't shift at all. So they obviously go in opposite directions and you'll observe it. They're opposite directions on the complex plane.
And that's why one or the other will be higher or faster than
Good for you. That's right. That's right. Yeah, there's more than one way to get the answer. I'm just trying to keep it, I built up this model of voltage dividers, so I'm staying there for now. And I'm mentioning the complex plane, but I'm not getting into phasors just yet. And in fact, Hayes barely touches phasors. He likes to keep the math as simple as possible. We'll get into it at some point. It's not easy to teach. Most kids who get to it in Physics 2200 don't understand what they did. I've been working on how to teach it. Okay, so let's see what we got here. What else do I need to tell you? So at the end of the day now, we don't need any of this math to just take some measurements. So instead of trying to measure the voltage across our standard, we're going to measure the VN with channel 1. We're going to measure the V out with channel 2. And I've just drawn in the ground here. Of course, the ground means that this is connected and that this is connected. And what we can do then, we can say now that we know that V out over V in equals Z2 divided by Z1 plus Z2. So we can cross multiply and we need to collect terms. So Z2 times VI minus V out equals Z1 over V out. And, oops, so then we can divide by this. There we go. So we can measure, that's how we measure Z2. And in fact, it's very similar to what we've done before. If you think about it for a minute, the denominator is actually V in R standard. And we have the, up here, the V out. And Z1 happens to be our standard. So we end up with V out over I, which of course then is the resistance or the impedance of Z2. But we don't have to do this anymore. We just need this equation here. So we'll see if we can tie this all together. So you guys are going to be making, oops. Wait a minute. Yeah, yesterday afternoon I got a wanging headache after my lecture and it's coming back. Although not as bad as yesterday. Okay, let's hold on a minute here. And I may stop and restart this recording. I don't like them to get too long. I'll do that because once I'm going to sketch out the table that I've given you, and then we're going to take a look at the spreadsheet. We're going to make a spreadsheet. Okay. So we're going to take a series of measurements. So I forget exactly what the table is that I put there. And for each of these, we're going to measure a V out and a V in. And we need a series of frequencies. And you'll notice now the table I gave you, it doesn't have any, like the one before did, because we need to figure out what frequencies we're going to measure. And all these are going to be peak to peak. That's another nice thing, because before we would have gotten RMS out of the voltmeter and peak to peak out of the oscilloscope, and that is a pain in the butt. Oh, and another nice thing about doing V out over V in, you may recall that we had some issues when the impedance of the voltmeter was comparable to the impedance of the thing we were measuring. By using the V out over V in, we circumvent that. So you may notice at some point you've set your function generator for a certain voltage in peak to peak. Don't just write that in everywhere. Because you may discover at some points that droops a little bit. But as long as you write down both V in and V out and get the ratio at some point, you'll be fine. So, before I go into the spreadsheet, remember, channel 1 in this setup is V in. And again, remember, you want V peak to peak. Channel 2 is V out. And where exactly you put the numbers on the table depend on what is your device under test. Okay, so I'm going to stop the recording. I'm going to leave this up there. And we can also take a small break, I think, because everybody, once you got the notes,